Hi, Algebra 2B students, how you doing? We're working on 8.5B notes today. This is average speed when you have two or more speeds going on at the same time, such as currents, wind currents, water currents, kayakers, boats, things like that. So what we're going to be doing, every problem is very different but uses the same ideas, so we will be in class doing all these problems together. So this video will be just to set up the problems in case you're at home trying it on your own. We won't actually solve the problems because they are rational equations that you learned how to solve in 8.5A. So we're just getting these set up for you. Again, very much the same and different at the same time. What we're going to be doing is using the idea that distance equals rate times time, right? You know that's true if you're going 50 miles an hour for 2 hours. That tells you you've gone 100 miles. This distance equals rate times time. Also, if you move some things around legally, becomes distance divided by the rate is time. Or one more way is distance divided by time equals rate. What I do for each one of these problems is I fill in a distance equals rate times time chart. And I always have two rows there's always two things going on. I have a trip upstream, downstream, I have two shuttles, right? So I always have two pieces of information going on that I'm going to collect for distance equals rate times time. And then using one of the formulas above in bold, that's the hardest part is how do I write this? What does it look like? We're going to write a rational expression depending on the question you are asked and the total units that you were given. And it really just takes practice, and that's why we do it together. So let's set some of these up together. So the first problem is an example that we work on, and it is a kayaker spends an afternoon paddling on the river. She travels 3 miles upstream and 3 miles downstream in 4 hours total. Notice it doesn't say how long it takes her upstream and downstream. I'm assuming it takes her longer to go upstream than downstream because she's working against the current upstream and the current is helping her downstream. Now in still water, the kayaker can paddle at 2 miles per hour on her own. They're asking what is the speed of the current, of the water. Let's call that C. All right, so I'm gonna make my little chart like you see above. And we have distance, rate, and time. There we go. Our two parts of our situation are upstream and downstream. There we go. Whoops, put two ends there. Let's see what we can fill in. Upstream was a distance of 3, and so was downstream. Now the rate upstream has two parts to it. The kayaker is going at a rate of 2 miles per hour, but the current is working against her, and we call that C. So 2 minus C, because she's working against the current of the river. Downstream, then, that would be her rate plus the current because they're working together. Now the time, I don't know the time for each of them separately, but I do know that it adds up to 4. So this kind of tells me that I need to write equations in terms of time, right? And that time was distance divided by the rate equals time. So here's what I'm going to do. I have the distance and the rate for upstream. That's distance divided by the rate, plus I have the distance and the rate for downstream, right? Distance divided by rate is time, and that is 3 over 2 plus C. And when I add up those two times, I get a time of 4. So here is the rational equation you will be solving. You do know how to get rid of these denominators by multiplying through. So work the problem from there. Okay, next. An airplane flying with a headwind. That means that the wind is going against the head of the plane. travels 1,000 miles from one city to another in 2 hours and 12 minutes. On the return flight with a tailwind, the total time was only 2 hours. So a tailwind means the wind is pushing behind, on the tail of the plane and actually helping it. That's why it only takes 2 hours. A headwind works against the head of the plane and actually slows it down more than you would think. That's why it takes 2 hours and 12 minutes. Find the airspeed of the plane and the airspeed of the wind. So I'm going to call P the airspeed of the plane and W the airspeed of the wind. Let's make a chart. Here we go. There we go. Distance equals rate times time. Notice what we have is we have the flight, it says from one city to another. So to first city, right, to the first city and then back. Okay, notice they say that they travel 1,000 miles to the city and back. There's our distance. Okay, the rate to the first city on the way there, there's a headwind, right? So it's the plane speed, and we subtract the wind speed because it's working against the plane. On the way back then, the wind is helping the plane, so that's P plus W equals the total rate. And, they give us the time. So this is 2 hours and 12 minutes. We're going to have to fix that because we need a decimal. And on the way back, it only takes 2 hours. Notice that 12 minutes is 1/5 of an hour, which is 0.2. So this is 2.2 hours as a decimal. Okay, I have two variables, so I need two equations. So I'm just going to do distance equals rate times time. Distance equals the rate times the time for on the way there, on the way back. Distance equals rate times time. Notice what we can do here. I am going to solve a little bit more since we haven't solved a system in a while. For the first equation, I am going to divide by 2.2 on each side. Make it a little nicer. 1,000 divided by 2.2 is 454.5. On the second equation, I'll divide both sides by 2, and that's 500 equals P plus W. There we go. So I divided the top equation by 2.2, the bottom equation by 2. Now, a great way to solve this equation is just to add up the equations because a variable eliminates. So notice on the left, that would be 954.5. Love you. Where are you going?
We're at Michael's to pick stuff up.
All right. Hope it goes well.
Me too.
Oh, that's right. It's Friday. Bye. Love you. That was my son, Alex.
Sorry, class.
They don't mind a bit. There we go. And then when you, so the left is 954.5. When I add up the P's, I get 2 P's. And when I add up the W's, they eliminate. And then we divide by 2. So the speed of the plane is 954.5 divided by 2, which is 477.25 miles per hour. Wow, that's fast. And I'm assuming that you could take either one of the equations here and put the P in to solve for the W. All right, our next problem, let's take a look. The next problem is a river barge travels at an average speed of 8 miles per hour in still water. The barge travels 60 miles up the Mississippi and 60 miles down the Mississippi in a total of 16.5 hours. What is the average speed of the current of the river? We'll call this C. So I don't know if it seems like it to you, but this is exactly the same as the kayaker with different numbers. Distance equals rate times time. So upstream, downstream, notice they gave us it's 60 miles, right? For the kayaker, it was 3. Our rate, the boat can go 8 miles per hour minus the current, right? Going upstream, going against the current. Downstream, the boat is going 8 miles per hour and the current is helping it. And again, we don't have a time, but we have a total time of 16.5 hours. I'm assuming it takes longer to go upstream than downstream. So again, we want to write, since we have a total time, we want to write equation in terms of time, just like the kayaker. Time is distance divided by rate. Upstream, distance divided by rate, plus time downstream, distance divided by rate. And when you add up those times, you should get 16.5. Again, you know how to solve this rational equation. Let's go to the next problem. There we go. A passenger jet travels from Los Angeles to Mumbai, India in 22 hours. On the return flight, it takes 17 hours. The difference is in flight times is caused by winds over the Pacific Ocean. If the jet's average speed is 550 miles per hour, what is the average speed of the wind? We will call that W. Let's get that chart going. Notice again, we have 2 trips. We're kind of used to that. Distance equals rate times time. We're going to call this LA to Mumbai and Mumbai to LA. All right, let's take a look. Do we have a distance? No, they don't give us a distance to Los Angeles to Mumbai and back, but we know they're equal to each other. Do they give us a rate? Well, I do know that the rate of the plane from Los Angeles to Mumbai is 550 miles per hour. And I do know that it's taking 22 hours. Okay. I also know from Mumbai to Los Angeles that for the same distance, the plane is going 550 miles per hour, but it's taking 17 hours. Okay, where's our variable W? I know that from Los Angeles to Mumbai, the rate must be 550 minus the wind because it's taking longer. And on the way from Mumbai to Los Angeles, the rate must be 550 plus the wind because it's taking only 17 hours. Now, what do I do here? This one's different. I only have one variable, and this says to me that the distances are equal, and distance equals rate times time. So if I do rate times time for the first row, that's a distance, and that equals rate times time on the way back, because we know the distances are equal. And this is not even rational. It's a nice equation you know how to solve. So go from there. Let's take a look at the next problem. See? A swimmer can swim 18 miles downstream in a nearby river for 3 hours. However, the return trip upstream takes 6 hours. Find the swimmer's average speed in still water and find the speed of the current. We will call that S and we will call that C. The speed of the swimmer and the speed of the current. Let's take a look here. I think we have upstream and downstream again. Distance equals rate times time. We'll go upstream and downstream. Okay, let's take a look. The distance 18 miles downstream and upstream, so they're going upstream and downstream the same amount. The rate when they're going upstream, that would be the swimmer's rate minus the speed of the current, and when they're going downstream, it would be the swimmer's rate plus the current. There we go. And let's see, they did give us the time. Downstream is 3 hours, upstream is 6 hours. Okay, so when you notice this, there's actually something going on here, is that notice on our third formula in bold that distance divided by time equals the rate. And I do have the distance and the time, and that should equal the rate. So let's take a look. 18 divided by 6 equals the rate S minus C for the first column. So that is 3 equals S minus C. There we go. For downstream, distance divided by time is rate. That's 18 divided by 3, and the rate is S plus C. And that is 18 divided by 3 is 6 equals S plus C. Now, we just solved a system, so I'm assuming you can do this. Notice if you add up these two equations that you get 9 equals 2 S's and the C's eliminate, and you can go from there. Next. This one is different, of course. 2 airplanes fly in opposite directions from the same airport. The second plane leaves a half hour after the first. So the second plane is in the air a shorter amount of time than the first plane. The second plane travels at a rate of 60 miles per hour faster than the first. Find the airspeed of each plane. If 2 hours after the first plane starts, the two planes are 2,015 miles apart. Well, this is different. Okay, let's do first plane, right? Second plane. Let's see if we can work this out. Distance equals rate times time. Let's take a look. Now, the airplanes are flying in opposite directions, which means that they are adding their distance up. And they do say, I don't have a distance for each, but I do know that the total distance is 2,015 miles, right? When they're going in opposite directions, the total distance is when you add them. This says to me, I'm gonna need a distance formula. Let's check our rates and times. So let's see. The second, the second plane leaves a half hour after the first. The second plane travels at a rate of 60 miles per hour than the first plane. Okay, let's call P the first plane speed. Okay, so the first plane, its speed I'm gonna call P. The second plane travels 60 miles per hour faster. So it is the speed of the first plane plus 60 miles an hour faster. It says that find the airspeed of each plane if 2 hours after the first plane starts. So the first plane has been in the air 2 hours, and we know the second plane left a half hour after the first, so it's only been in the air 1.5 hours. So notice this one's very different. Let's go back. Let's see if we got everything. 2 airplanes fly in opposite directions from the same airport. The second plane leaves a half hour after the first. The second plane travels at a speed 60 miles per hour faster than the first plane. Find the airspeed of each airplane if 2 hours after the first plane starts, the two planes are 2,015 miles apart. I think we've got it all. Okay, I know that I have to add up two distances to get 2,015. That would be rate times time. There we go. Rate times time is the distance for the first plane. Rate times time is the distance for the second plane. And there we go. You know how to solve this equation from there. Last one. Let's take a look. What else do we have? I have something a little different. And so I wanted to, if it's okay with you, just do this problem a little differently. We can certainly use the chart method, but I want you to know that if formulas aren't working for you, we can try other ways. So a hotel 35 miles from an airport runs a shuttle service to and from the airport. The 9 a.m. bus leaves for the airport traveling at 30 miles per hour. The 9:15 a.m. bus leaves for the airport traveling at 40 miles per hour. So even though this shuttle, the second one, left later, it's going faster. So at some point it might catch up. How far from the hotel will the 9:15 a.m. bus catch up to the 9 a.m. bus? So let's do this a little different. Let's do a chart. Okay, here we're going to do the time. And let's do shuttle 1 and let's do shuttle 2. Okay, so at a time of 9 a.m., the first shuttle, how far has it gone? We're trying to find the distance it's gone and the distance for the second shuttle. Well, the 9 a.m. shuttle is just leaving, so it hasn't traveled at all. Same with the second shuttle. Okay, now I see that they're talking about 15-minute increments, so let's go to 9:15. Now let's remember the first shuttle is going at 30 miles per hour, and the second shuttle is going at 40 miles per hour. Okay, so 15 minutes later, that is 1/4 of an hour, right? How far did the shuttle going 30 miles an hour go? Well, it's going 30 miles in 1 hour, and it's gone 1/4 of an hour. So let's see, it made it 1/4 of 30 miles. It has gone 7.5 miles in 15 minutes. Okay, the second shuttle hasn't left yet. Still at distance 0. Let's go to 9:30. Well, what we have found is the first shuttle seems to be going 7.5 miles every 15 minutes, right? And it's gone 15 more. So that's 7.5 plus 7.5. That shuttle is now at mile 15. Now let's go to the second shuttle. It is going 40 miles per hour. So it's only been on the road 15 minutes. That's 1/4 of an hour. And let's multiply that by 40 miles per hour, right? We know that rate times time gives us a distance. Well, 40 divided by 4 is 10 miles. So this shuttle is going faster and gets 10 miles done every 15 minutes. The first shuttle only gets 7.5 miles done every 15 minutes. So shuttle 1 is at 15 miles, shuttle 2 is at 10 miles. Let's see when shuttle 2 catches up. Let's go 15 minutes more to 9:45. That means the first shuttle adds 7.5 miles. It's at 22.5 miles from the hotel. The second shuttle gains 10 miles every 15 minutes. So it is getting closer. It's at 20 miles from the hotel. Notice they're getting closer. Let's go to 10 a.m. Right, 15 more minutes. The first shuttle has gone 7.5 more miles, and that is a total of 30 miles it's gone. The second shuttle is at 20. It added another 10 miles, so it's at 30 miles from the hotel. So notice the second shuttle caught up to the first shuttle 30 miles from the hotel. So sometimes when you can't write a formula well, try something else. Just go, you know what, I'm going to make time go by. I'm going to make myself a little chart to solve the problem. Have a great day.